Okay, welcome. We are still continuing on here through chapter 2. Last time we talked about some things, chemistry, like I imagine, but we talked about really how to take proper measurements. And as we talked about, remember that when you do take a measurement, you want to make sure that you always look at the scale, the piece of equipment that you're using, as obviously different pieces of equipment will have different scales. And typically, when we do look at the scales, there's kind of two sets of numbers, large numbers and small numbers. And like we did here with like a ruler, for example, large numbers are usually marked. So this would be something like 1 centimeter. We also want to count up really how many small markings there are between each of those large markings. We do start counting, as we talked about, past that last large marking, and we go to the next large marking. And in this example, hopefully I drew enough dashes, but there should hopefully be 10 of them there. And that means, again, that each of the smaller markings are 1 centimeter or 0.1 centimeters. Remember that if you can correctly sort of identify what the smallest markings represent in terms of their value, you can very simply divide it by 2, and you'll get really, sometimes they refer to as plus or minus, how far you should take the reading on that particular piece of equipment. In most cases, it is usually one more place to the right of the smallest marking is where you can take it. But if you're not sure, again, you could just kind of divide it out. As I mentioned before, for me, I don't need you to put the plus or minus, 0.05 or anything like that on measurements. But you do need to take them obviously to the proper digits. When we do record a measurement, in addition, obviously, to units, we always record all the certain numbers. And we record that first uncertain number, which is sometimes referred to as the estimated sort of digit. And remember, really, kind of all those things together is what makes up significant figures. So when we do that, when we take a measurement, there should, as we talked about, be some numbers that no matter peak, that everybody should agree that is at least this much. And again, there's going to be some type of estimation or uncertainty in a certain digit, and you do need to record that digit as well. We talked about as well how to count significant figures, and more so as well to do calculations with significant figures. And remember that when we do calculations with significant figures, there's sort of two categories that usually it falls into. Either you're multiplying or dividing. And when we do multiply and divide, it is significant figures that we are looking at, and it is the least amount of significant figures. So your least number of significant figures you're doing is really how many significant figures your answer should have. Frankly, it's because it's probably your worst measurement, for example, in this group of numbers. So your overall calculation is really only as good as your worst sort of number that you have. And that goes for both multiplying and dividing. You want to look at significant figures, and that is different than the other sort of grouping of math that we do, which is adding or subtracting. When we add and subtract, we're actually looking at decimal places, and it also is the least number of decimal places. So remember that if you're adding or subtracting, it is not significant figures that you're looking at, actually decimal places. And for the same reason, the least number of decimal places is pretty much going to be your crappiest measurement, for lack of a better description there. And that's going to limit how good your overall calculation is essentially going to be. Remember, though, if you add certain numbers together or subtract certain numbers together, bless you, although you do go to the number of decimal places, that also means that that number has a certain amount of significant figures, which would be important if you took that number and then, say, multiplied it or divided it. So we also talked about the idea that if you do multiple sort of steps in a calculation, you do want to kind of keep track of your significant figures all the way through your calculation. We also talked about not rounding too much along the way. You could keep a guard digit or a few extra digits and then just kind of keep track of where you're at and then kind of clean up at the end. Usually sort of that last calculation is sort of what's going to perhaps determine where you end up. And you do want to do your significant figures sort of in the order of your calculation that you did. So I think we did an example where we multiplied first and then we divided, then we added or something like that. So again, when we multiplied, we would look at significant figures, figure out how far we should take the reading to, not round, then divide, which is still looking at significant figures, and then we add it at the end, which is looking at decimal places. And again, based on the significant figures we should end up with the multiplying and dividing, that's going to have a certain number of decimal places that we would look at when we did the final adding. So you want to kind of keep track of all that along the way and clearly round too much. Speaking of rounding, we also talked about not doing crazy rounding, right? So although you do want to hit the right number of significant figures, you don't want to round so much that you really change the meaning of the numbers. I think maybe we looked at 12,000 or something like that. And again, we were shooting for 3 significant figures. So remember that 12.0, although it is 3 significant figures, there's a very big difference between 12 and 12,000 in terms of the meaning of the number. So sometimes that does happen with people when they try to get the right sig figs, they kind of overdo it on the rounding and change the meaning. One way that you might need to get around that or to get to the right number of significant figures, as we talked about, is with scientific notation, which you could kind of control how many significant figures that you would need. Stuff there we talked about last time. All right, so continuing on here with, I think, where we left off. I think we saw a table like this earlier on in this chapter, but again, a reminder. You are responsible, right, for stuff, as they want you to kind of know these things by heart. So this is a pretty good table. I would say through your journeys of chemistry, you'll probably use most of what's on this table in terms of prefixes. I don't know, deci sometimes doesn't appear all that much, but the rest don't really do. And then here we see a lot of kilo, centi, milli, not a lot of micro, nano. You see a lot of that in 1A as well when you get there. But you do need to be able to do this. And as we talked about last time, we do want to make sure that, you know, if you do use this, that you do use it correctly. So mega, right, is 10 to the 6th. Remember that that really is 1 times 10 to the 6th. If you need to punch that into your calculator, it's essentially what that number represents. And when we use that number, it is how much there is in the base unit, again, to one of the prefix units. So if we had megagrams to grams, there would be 10 to the 6 grams in 1 megagram, as that is our prefix unit, that is our base unit. And as I think I might have mentioned last time, it's super common. People always want to kind of use these guys backwards, where they'll go something like 10 to the 6 megagrams is 1 gram. So again, make sure that you do use it correctly. Again, something like milli here, which is 10 to the minus 3. That means if I had something like milliliters to liters, there would be 10 to the minus 3 liters in 1 milliliter. So again, in one of the prefix units, that's what the sort of exponent value represents of one. So like I said, you might want to start this so you know it. And I would say probably out of all these, this one you probably see the least, but definitely we'll see a lot of kilo, centi, milli. And you should know these, as you will definitely see them as you continue your journey through. So we talked about some important length equalities, and a reminder that an equality is basically 2 things that are on different scales but represent the same amount of something. So 1 meter is 100 centimeters is the same thing. That definitely pops up a lot. 1 centimeters are 10 millimeters. I think we looked at that when we were looking at a ruler, right? The bottom part there of the ruler. So those 2 are, again, pretty important ones. In terms of volume, I would say definitely, as we might have mentioned before, that's the pretty one you should commit to memory really quickly. A lot of times we do measure volume, and a good number of times, a lot of formulas and stuff like that require you to convert it to liters. So that kind of milliliters to liter conversion, and also going liters to milliliters is something we use a lot through chemistry. That you know that one. The other sort of relationship similar to your lab that you did, and we talked about it, is sort of with a milliliter and a cubic centimeter. So remember that if you have something like your little wooden cube you used last week, I think, if you take 3 length measurements, like all in centimeters, we'll give you a cubic centimeter, which is a volume. So typically speaking, if you take a length measurement in cubic meters, cubic centimeters, again, that will give you a volume. Also a reminder that the individual measurements here are all length measurements, right? So those are all individual length measurements, but when we multiply them together, we do volume. Really important relationship. Again, 1 cubic centimeter is equal to 1 milliliter. It's a 1-to-1 conversion. Although a CC that we might have talked about as well last time is also a reference to a cubic centimeter, and oftentimes used, say, in medicine. And here in chemistry, cubic centimeters is cm3, and the milliliter, again, are very common units that we do come across. In addition, we want to make sure that when we do take a reading, we do read a liquid, for example, from the bottom of the meniscus, right, as if here's another sort of scale right on our graduated cylinder here, and things are different depending on the graduated cylinder or glassware. That's 90. That is 100, which again means we got 10 milliliters as our large sort of difference between our markings. Individually here, smaller markings, we got 1, 2, 3, 4, and 5 markings, which means each of the small markings on this particular one actually is 2 milliliters, as that would be 92, 94, 96, 98, as you kind of go up there. That means, again, if you're not sure, you just divide that by 2, and that tells you in this particular case, one of these sort of exceptions, you cannot necessarily go one more place to the right of the smallest marking. Here, the best you could do is hit a full number. One similar to this, again, if you found yourself, for example, 92 and 94, 93 sort of between there. Again, there's not enough room to visually figure out where 92 ends, where 93 begins, and so that sort of thing. So it's just too big of a span and not enough room between those two markings to sort of figure it out, as opposed to when, say, like a 1 unit difference between markings, you're able to go, okay, it's halfway there. So it's like, 5 or something like that. Any questions on that there? Obviously here, these are probably big ones that you should know for sure. Kilograms, 1,000 grams, and 1 gram is 1,000 milligrams. These are sort of the larger values that you could use by just dividing that kind of 10 to the minus 3 to the other side, and you get to a larger number. So you can remember the larger value, you can remember the kind of 10 to the minus 3 version of it, whichever way you want to remember it. Obviously, we use a balance there to do that. All right. So here's some of those conversions. So let's talk about the next really important thing, which is writing conversion factors and really doing conversions, and basically the way that they would like you to learn and they expect you to do calculations in chemistry, which is really dimensional analysis. And dimensional analysis, as we'll talk about, is a way that we set up problems where we use conversion factors and we use units to have everything cancel out. So any type of equality, as I mentioned before, is basically 2 things that represent the same amount but are on different units. So if we just took a fairly straightforward one, like 12 inches is 1 foot, that is an equality. And from any equality, you could write 2 conversion factors, which are really just fractions. We could say 12 inches over 1 foot, or if we needed to use it the other way around, 1 foot over 12 inches. These would be our conversion factors. Now, in most cases, you will not use both conversion factors in a problem. Otherwise, you will be undoing your calculation, basically. So you will just use the one that works. And how we set these things up is what's referred to as dimensional analysis. So for example, if I had a certain unit here, like unit A, and I wanted to get rid of unit A and end up at unit B, for example, I would use a conversion factor. And although when I write this like it is here, it is not really written as a fraction. You could kind of think of it as a fraction, like it's over 1. And the importance of that is basically unit A is up on top. And when we use dimensional analysis, pretty much all we are going to be doing is multiplying by, which means that when we want to get rid of a particular unit, we basically go in the opposite location of that unit, and that will cancel it out. So if I were to do this and use a conversion factor, I would want to use unit A on the bottom and unit B, which is maybe what I'm looking for, up on top. And what we're going to do mathematically here is multiply, and whatever's over here on the bottom, we're going to divide, basically. And what that will do is essentially cancel out unit A. They will cancel each other out. It is the same idea if you took 2 divided by 2 equals 1. If you have unit A up on top and unit A on the bottom, they also will cancel each other out and basically become 1. So that is how the units basically cancel out, just like you were dividing the same number on top and bottom. You're dividing the same unit on top and bottom, they would cancel. You would be left with like unit B. So for example, if I had 43.5 inches and I wanted to know how many feet that was, I would start with my 43.5. I would go to my conversion factor, and again, my inches are up on top, which means my inches need to go on the bottom. And I'm going to use my conversion factor to do that, which would be 12 inches is 1 foot. Once again, here, inches on top and bottom will cancel each other out. We're going to multiply and then divide. In this case, there's not much to multiply since we're multiplying by 1. But if it makes you feel better, you can multiply it by 1, hit equals, and then divide it by 12 and hit equals. And that will give me 3.625. The units that are left over are feet in this case. Now, in terms of significant figures for the answer, because we are, when we set things up in dimensional analysis, pretty much just multiplying and dividing, it is significant figures that we're going to be looking at. So if you remember, something else that we talked about last time was the idea that there are certain numbers that are measured numbers, which has a certain significant figures, and there are certain numbers which are considered exact numbers, which essentially can have as many significant figures as you want. Exact numbers are things that are counted, if you remember, and also definitions, like 12 inches is 1 foot, basically. So when we have a calculation that involves something that's considered an exact number, we actually do not need to worry about it in terms of the significant figures when we do that calculation, and we just sort of ignore it because it could have as many significant figures as you want. That means that we essentially would ignore this, and we would look here for our significant figures, which is 3. And that means we should go here and round up, and that will give us 3.63 feet, which has 3 significant figures as our proper answer in this particular case. Any questions on that there? How they want you to show your work, and when they say show your work, that is what you need to do. You need to show your work with the units, the conversion factors, all the units canceling out, proper number of significant figures. Any questions on that there? Okay, so let's take a look at, this is another example, like if we had $1 is equal to 100 pennies, a reminder that obviously that represents the same amount of money. And we could write two conversion factors, 100 pennies over $1, or $1 up on top, 100 pennies on the bottom. So once again, you know, if we had dollars and want to know how many pennies, we'd use the guy on the right. If we had pennies and $1, we'd use the guy on the left there. Opposites essentially will cancel each other out. So let's take a look at some of these common equalities. And remember that there's two types of units. There's the English, which is also sometimes referred to as US units, and pretty much the metric units. So when we talk about using equalities or conversion factors that are exact numbers, there are a couple of things we want to think about. The first thing is if it is a English to English conversion, you're good to go. You could consider that an exact number. So if you're using anything there in the first column, for example, those are all English to English conversions. They're considered exact numbers. You don't have to worry about those guys in your calculations. Also, if you're doing some type of metric conversion, like the middle column there, considered exact numbers, so you don't have to worry about them as you're doing calculations. By the way, this is also a good table. A lot of this stuff we come across a lot, so you do need to kind of know most of what's on this table. When we get to the crossing over between English to metric or US to metric, this is really the situation where you do have to kind of take into account the significant figures in that conversion factor. So here, in most cases, you do need to look at significant figures. I will fix my conversion here because I got yelled at. So let me give you the right one here. They want you to know 453.6 grams is 1 pound. So we'll fix that there. So they do want you to use 453.6 gram pound as a conversion for that. Now, in US, there are a couple of these conversions which are considered exact numbers. The two popular ones that you probably come across is this one. So if you are using 1 inch, is exactly 2.54 centimeters. And that's why on a lot of books, you'll see it written like that, like exactly next to it. It's considered an exact conversion. You don't have to worry about significant figures. And for us here, since they want you to use this number for grams to pounds, you could also consider that one a exact conversion as well. So don't about using that. Now, if you're using some other metric English sort of conversion going either way, you do have to look at the actual significant figures in those guys. So which numbers should you look at? Well, in most cases, one of those conversions should be like 1 and the other one should be an actual number. So you would look at the one that is the actual number and not the 1. Otherwise, everything would be one significant figure. So you wouldn't look at the one part of it, but you would look at the other. So for example, if we pull out, say, this one here, we'll take that one. And let's just say we had 4255 milliliters, and we want to know how many quarts that would be. So we would use this. This will give us two conversion factors, 946 milliliters over a quart. Our 1 quart is 946 milliliters. So here we would go opposites, which means milliliters needs to be on the bottom. So we will roll with that one, which would be 1 quart, 946 milliliters in this case. Once again, the milliliters are going to cancel. We're going to basically take 4,200, if I punch it in right, 4,255, and we're going to divide it by 946. Hit equals going to give us 4.497885835 on my calculator, which clearly is not the right number of significant figures. Also a good reminder, right? Your calculator doesn't give you the right number of significant figures, so you do need to fix it. So in this case, we do need to look at this conversion factor here. And we again would look at the real number, not the one part of it. And in this case, that would be 3 significant figures. We would also look at our original number, which is 4 significant figures, which means technically speaking, we should end up at 3 significant figures based off of that conversion, which would be 4.50 as we would go here and then round up, right? Because of the 7 quarts. Question on that there. So that is the one place where if you're doing some type of conversion, dimensional analysis, and you're using a metric to English sort of conversion, you should look at the significant figures in the actual conversion factor. I will say, unlike this example here, probably most of the time, even if you need to look at the significant figures of that kind of conversion factor, not all the time, but a good majority of the time, that first number that you start with usually has pretty close to the right number of significant figures, but again, not 100% of the time. Obviously, this would be an example where it wouldn't be 100% of the time. So if you're using English to English, you're good to go. Don't worry about it. Metric to metric, pretty much good to go. Most English to metrics, again, you should look at it. The other place where if you're using some type of conversion factor and you should look at the significant figures is if it's a conversion factor from the problem itself. So somewhere in the problem, maybe they say, hey, you're driving 22 miles an hour or something like that. That clearly is not a standard conversion like we always are going 22 miles an hour. That's specific for that question. You should look at the significant figures in that. Sometimes within the problem itself, they will give some values that you'll use as a conversion factor. And usually in those situations, you do have to look at the significant figures. As I mentioned before, a good amount of these guys we do come across a lot. So, learn a good amount that's on this slide will probably serve you as you're going through your classes. Now, when we do talk about it here in just a second as well, but when we do set it up with dimensional analysis here, I've only really done one conversion, but sometimes you'll do multiple conversions in a row. A couple of things in terms of math-wise and punching into your calculator. Usually you want to multiply, or you can multiply as many numbers as you want that's on top all the way across. You can multiply as many as you want. When you get to the end, it's a good idea to hit equals on your calculator. And then when you come back, if you have multiple numbers on the bottom that you need to divide by, if you want to kind of get the right answer all the time, you should divide by each of those numbers individually, like divide by the first number, hit equals, divide by the next number, hit equals, divide by the next number, hit equals. What happens sometimes when you have a lot of numbers on the bottom and you want to divide it, people sometimes want to punch that all into their calculator at once. And if you do not use parentheses correctly, which a lot of people do not do, you will get the wrong answer because your calculator will do the wrong math. So if you want to always be safe, however many numbers, all multiplication, multiply as many as you like. And if you have multiple numbers come back through, divide by the first one, hit equals, divide by the next. You will always get sort of the right answer if you do it that way. Any questions on that there? All right, so again, getting our conversion factors from equalities are important. So 5,280 feet equals 1 mile. By the way, that pops up a lot along the way. So that's a good one to have in your head. Again, gives us 2 types of conversion factors, 1,280 feet over 1 mile. Our 1 mile is 5,280 feet. Now, sometimes we're given things in words that have multiple units, like, for example, driving 65 miles per hour. Something per something is basically 2 sets of units. Usually the number stays with the first unit, 1 usually. So when we say we're driving 65 miles per hour, that means in 65 miles, it will take us about an hour to do that, right? Or in 1 hour, miles. Also, sometimes we need to convert both units, right? We may have a conversion factor where we have to do that. So for example, if we had our 65 miles per hour and we want to know how many feet per second that would be, we would actually have to do 2 types of conversions, right? We need to convert the top unit and we also have to convert the bottom unit. And we also need to think about how to get there, right? What is a good pathway to get there? For example, we could use the previous one. 5,280 feet is 1 mile, which obviously gives us 5,280 feet over 1 mile as a conversion factor. Our 1 mile, 5,280 feet. Dare I ask it, but hopefully we know in 1 minute, there's how many seconds? 60 seconds, yes. And in 1 hour, there's how many minutes? 60, that's good. And hours in a day is? It is 24, not 60, which is a very common mistake people put on exams. 24 seems like enough hours in a day. So it's not 60 along the way. Obviously, each of these will give us some conversion factors that we could use. Obviously, here, 1 minute over 60 seconds, or 60 seconds over 1 minute, and then our 1 hour over 60 minutes, are 60 minutes over 1 hour. So these are all the conversion factors there on the right that go with our equalities. Obviously, these are all the conversion factors. So if we were going to do this, the importance of setting this up through dimensional analysis, besides the fact that that is the way they want you to show your work, is it really can help with the math and doing the math correctly. So if you set this up as 65 miles on top over an hour, I'm going to do the top conversion first. And by setting it up like this, I could clearly see miles are up on top, which means if to get rid of it, I need miles on the bottom. And that means I do need to use the conversion factor here to do that. That would give me 5,280 feet is 1 mile. If I stop the calculation right at this point, I would be in units of feet per hour, which is one, right? So I got the top part all good to go. Now I just need to kind of convert the bottom part there. And by setting it up like dimensional analysis, which you should do, it does make us understand very clearly that we can see hours are on the bottom and not the top. And sometimes when people do not set it up in dimensional analysis, which you should not do, they have no idea where that hour is it on top, is it on the bottom? And the importance of that is they're not really sure, should they be multiplying, should they be dividing, what they should be doing when they do this. By setting it up like this, we could clearly see it's on the bottom, which means to get rid of it, I need hours up on top, and we will do that. That will give me 1 hour is 60 minutes. Hours will cancel. If I laid it up right here at this point, I'm in feet per minute, which is close to what I want. I need to go one more to get me to seconds, but I could clearly see, because I set it up correctly, my units of minutes are on the bottom, which means to cancel them, I need to go opposite and have minutes up on top. So I would use this as my conversion factor to do so. And that would get me 60 seconds. I'm sorry, that would not get me that one. That would circle the right one, would probably be good there. On here. From my minutes, and that is what I want. That is the right one. I just wrote it backwards, I think. All right, so up on top is minutes, so we do want 1 minute up on top, and our 60 seconds there on the bottom. Minutes will cancel, and now we have units of feet per second. Now, mathematically, what we're doing is we are multiplying, once again, everybody that is up on top, and we're coming back here and dividing by everybody that is on the bottom. And if we do that, pretty much is 65 times 5,280, hit equals. Here I'm going to divide it by the first 60 and hit equals, divided by the second 60 and also hit equals. And that's going to give me 95.333, a bunch of threes. Units are feet per second. Now, in terms of significant figures, what's the things that we should look at? Well, if we look at this here, I'm not going to worry about that because that's an exact number. I'm not going to worry about that because that's an exact number. I'm really not going to worry about that because that's also an exact number, which means that is the only number I got going on at this point, which is 65. And that is two significant figures. And that means we should end up right about there, are at 95 feet per second. Yeah. Any questions on that one there? So this is dimensional analysis. This is the way you need to show your work. And to get full credit, that is what you need to show. Now, do you need to show all the conversion factors, the equalities? The answer is not really. You don't. If it helps you, do it. But for credit and full credit, as long as everything's correct, you need to show all this. The setup where you could clearly see the conversion factors, the units, and everything canceling, and clearly the proper significant figures on the answer there. Any questions on that there? Again, if it helps you to do all the other stuff, do all the other stuff. What's the difference? But you don't necessarily have to. All right. Couple more things looking at conversion factors. 91 octane, 305 a gallon. That's clearly an old slide. By the way, that was expensive back then when I did it. Just for reference point. Like one back then. So that is 1 gallon is $3.05. Would love that. What that is. Our $3.05 is 1 gallon. Now, another really common thing that we come across in chemistry that we oftentimes need to turn into conversion factors are percentages. So a lot of times we something and we want to turn that into sort of a usable conversion factor. And the easiest way to turn sort of a percentage into a usable conversion factor is a lot of times to assume that you have 100 of it. Like if you got a 90% on the exam, you probably got 90 points out of 100, right? So it's the same number. If you assume 100 of something, it pretty much keeps it the same number as the percentage, which makes the math a lot easier. You can really assume as much as you want, but 100 keeps everything the same. So for example, fat per mass, we could do the old metric system there, 12 kilograms of body fat over 100 kilograms of body mass, or 100 kilograms of body mass over 12 kilograms of body fat. We could also do more of an English sort of conversion, 12 pounds over 100 pounds of body mass, or in 100 pounds of body mass, there is 12 pounds of body fat. For example, if you were given something like 4.25% by mass. Mass to mass is what the M/M means, mass over mass, of say sodium chloride solution. What that would mean if you wanted to kind of turn that into a usable conversion factor, you would assume that you had something like 4.25 grams of sodium chloride in 100 grams of solution. So that's just an easy way to turn that into a usable conversion factor. You could also flip it around. In 100 grams of solution, there would be 4.25 grams of sodium chloride. So a lot of times in chemistry, we are given things in percentages. And again, just assuming that an easy way to kind of turn it into a usable unit. Any questions on that there? And as you can see, it doesn't really matter the units that you choose, right? They're all basically the same. You could do kilograms if you needed kilograms. You could do pounds if you needed pounds. You could do grams and grams if you needed that. So you could kind of just turn it into a usable number regardless of the units that you may come across. So we kind of did examples of this, but ultimately problem solving, dimensional analysis, that is the way you got to show your work here to get full credit. And it is just an easy way to do it and to think about how by keeping them, on top and bottom. It helps with the math part, like the previous example where we had the 60s on the bottom. I can't tell you how many people will be multiplying those 60s because they really don't know what it is or where it's at. So it helps keep the math kind of equal for you and easy to figure out what you should be doing. And besides the fact that you have to do it that way, that's a good way. Here are some of the steps that you could follow to solve these problems. A lot of times it's helpful to write out what is given to you, write out what you want to find. You want to think of a pathway to get you to your ultimate goal. Now, they are conversions, just so you know, because they are conversions, the pathway that you choose may be different, and you can't get the same outcome pathway you choose. So there are multiple sort of ways that perhaps that you could do the same type of conversion problem, and you should be able to get the same answer, regardless of which pathway you choose, as long as you choose real conversions and not ones you make up. So if you choose real ones, regardless of which sort of pathway you choose, you should end up with really the same answer at the end. So you want to write what you were given, write what's fine, equalities, what conversion factors. Again, set up the problem so you can see the units cancel, and you should solve the problem to right number of significant figures. Once again, for full credit, those last two is really what you got to make sure that you show as your work. All right, so looking at a pretty straightforward one here, we have how many pennies are in $3. Obviously, we could have our equality and our two conversion factors. So here we would start with our $3. And once again, we want to go opposite to cancel. So that will give us 100 pennies is $1. Once again, we're going to multiply and come back and divide. Dollars will cancel, going to give us 300 pennies in this case. Now, in terms of significant figures, we are not going to look at this as that's obviously an exact number, which means right there is one significant figure. And my answer has how many? I wrote it as. How many significant figures in my answer? One, yeah. So there is no decimal point written, right? So only the 3 in there. If we did put a decimal point, then it would be 3, and the incorrect number of significant figures, right, based on our calculation. So that does have just one significant figure to match our 1 sig fig there and our 1 sig fig there. Any questions on that one there? All right, so why don't you try one here? You go to the AM PM, get yourself 32 fluid ounces of drink from the Thirst Oasis. Crushed ice, cubed ice, your choice, but I think we all know crushed ice is the way to go. How many gallons of Diet Coke did you drink here? Yes. All right, so set it up using those equalities, think about the conversion factors, and set it up using dimensional analysis so that you can see everything cancel out and see what you come up with here. Okay, let's take a look. Once again, we want to think about a pathway to get us from fluid ounces to gallons. So we could go from fluid ounces to quarts, quarts over to gallons. These are the equalities to which we could get these conversion factors here. And once again, we were not going to use them all. Also, again, a reminder that on exams and quizzes, that's the question, right? You don't get any of the other stuff. Just happens to have it here in our lecture. All right, so we're going to start with our 32 fluid ounces. We're going to set this up dimensional analysis way, which means my fluid ounces are up on top, which means I do need it on the bottom here to get rid of it. So we're going to use this conversion factor here. That gives us 1 quart is 32 fluid ounces. Fluid ounces will cancel. Once again, if I stop right at this point, I'm in units of quarts. Seeing that it is clearly up on top helps me understand that all I have to do is look for the opposite, which is that one. And that's going to give me my right conversion to use in the right way. And that's going to give me 1 gallon is 4 quarts. Once again, the quarts here will cancel. Going to multiply what we got going on top. Once again, here, come back and divide by what's on the bottom. We essentially have just 32 up there. If you want to multiply it by 1, you can, but it's not going to change. We're going to divide it by 32 and hit equals. And also divide it by 4 and hit equals. And this will give me 0.25 gallons. And that is the answer. The answer is not 1/4 because it makes me think you're too lazy to punch that in your calculator. Give the answer as a fraction. Always divide it out. Take it to the proper number of significant figures. Not so bad in this case, but you shouldn't do it. But I've had people write something like 325 miles over 615 hours. I'm happy with my answer until they get the X. Yes, so don't do that. Divide it out. Never leave an answer sort of in a fraction. Make sure that you do get it to a number. Now, significant figure wise, really don't have to worry about it here. Exact number, don't have to worry about it here. That defaults us back to our sort of our original number, which happens a lot. That's two significant figures there for our answer. Any questions on that? Once again, in terms of full credit, everything on the bottom here is what you need to show, okay? All right, let's take a look at a couple more here. Just make sure we have an antibiotic doses that's given 500 milligrams. What is, how many milliliters is it if it's 250 milligrams in 5 milliliters? So see what you come up with here. Okay, so this is a situation where we are given sort of a conversion factor here in the actual problem as 250 milligrams in 5 milliliters. And we could use that as a conversion factor, as we see there, 250 milligrams over 5 milliliters. We could also flip it around if we needed to here and use 5 milliliters up on top and 250 milligrams on the bottom. So we're going to start with our doses we want to give, which is 500 milligrams. We're going to use that conversion factor that was given to us opposite, which actually means we do need to flip it around and use it like this. That's going to give us 5 milliliters is 250 milligrams. The milligrams will cancel. Once again, we're multiplying and dividing here. So that's going to give us 10 milliliters. First off, any question on the calculation? Significant figure wise, do I need to worry about the significant figures in this? The answer is yes, because that is not a true conversion factor, right? That's some type of conversion that was given to you in the problem. So you should look at the significant figures here. And how many significant figures we got going on there? We do have 2 on both of them. Did you have a question? Mm-hmm. Yeah. You don't. So I just did that originally to put it like, yeah, there's nothing underneath there. It's basically 1. So if it helps you to put 1 and so you can see that's on top, you can do that. If it's just a number by itself, you could kind of just assume that it's kind of the numerator. It's up on top the units. But if it helps you kind of keep everything organized, you could kind of just put it over 1 if you want to, but you don't have to. Yeah. And in this case, there were not 2 units. When we do have 2 units like the miles per hour or something like that, it's always, again, the number stays with the first unit and that's on top, and the second unit ends up on the bottom. In this conversion factor here, we actually have 2 numbers, and we do have to keep obviously the numbers with the appropriate units in the right spot. When we do this here, we do have 2 significant figures actually on both parts of that number. And over here, we actually have 3 significant figures, which means we should end up with how many here? How many significant figures should we end up with? 2. Do I have 2 significant figures the way I wrote that? I do not. I only have 1, so I do need to lay up something maybe like a decimal there, right? And now I will have 2 significant figures. Or if you want to do a little scientific notation, you could do 1/10 of 1. I will also give you 2 significant figures. Any questions on that there? Okay, so let's take a look at a couple more here, I think. All right, during surgery, a patient gets 5 pints of plasma. How many milliliters of plasma were given? Here's a few conversions or equalities. Let's see what you come up with on this one. Okay, so let's take a look. Again, we want to think about our path. We're starting with pints. We want to end up in milliliters. So one pathway is we could take our pints to quarts, and then from quarts, we could take it over there to milliliters using these equalities and obviously these conversion factors to do so. If you wrote out the conversion factors, these are really your 4 that you have to choose from in this case. Here we're going to start with the 5 pints. And once again, not written as a fraction, but the units here are up on top, which means to get rid of the pints, I do need it on the bottom, which means I do need to use the conversion factor here like this. 1 quart is 2 pints. At that point, the pints will cancel each other out. We're left with quarts as our unit, which again, we could clearly see are up on top. So we want to get rid of those. So we got to go opposite, and we're going to drop it there on the right there. That will put our quarts in the opposite location. That's going to cancel out our quarts. Once again, multiplying across the top here, making sure to hit equals at the end. Coming back and dividing by the bottom, also making sure to hit equals. Going to give us something on our calculator of 2365 milliliters. So let's talk significant figures here. Do I need to worry about this one? The answer is yes. That's an English to metric conversion. I should look at the actual number here, which is 3. How about this one? I do not need to worry about that one. Here, I do need to worry about it, which is 2. And once again, because of dimensional analysis, all you're doing is multiplying and dividing. It is significant figures we're looking at, and 2 is the smallest, which means we should go here. A little bit of a round up on that. 2,400 milliliters in this case, yeah. Again, you could also do a little scientific notation on this one if you wanted to as well. 2.4 times 10 to the 123 milliliters. Remember that when we do write, as we talked about, any number before the times 10 part are significant. So that would be the proper way to write in scientific notation. If I wrote as 2.400 times 10 to the 3, how many significant figures would I have? If I wrote 2.400 times 10 to the 3, I would have 4 significant figures, right? So remember, putting in extra zeros in certain situations is not always good. Yeah, especially in scientific notation, because they will count as significant figures. So we do want to be careful of that. Question on that. All right. Take a look at this one, see how we do. We are stranded 125 miles away from home. Seems like a nice day. Let's go for a walk, shall we? We're going to walk 55.0 feet per minute. How many days am I walking if I don't stop and I make it in one piece, I suppose? Yes. All right, so see how you do. Okay, so let's take a look, see how you're doing. So we're going to walk 125 miles. We're actually given, once again, here in this particular problem, another sort of conversion factor, which is that we're moving at 55 feet per minute. We could use it like it's written there, or we could flip it around if we needed to. A minute is 55 feet. That is basically a rate, right? How far you're going in a certain period of time, and we are going a certain distance. That's what we're going to use really to go from distance to time, which is ultimately what we're looking for, because we're looking for how many days, which is a unit of time. We do have a problem though. We got some unit situation here. I got miles on one and feet on the other, which means we cannot use them exactly together the way they are. We do have to do a conversion. You could either convert miles to feet, or you could go feet to miles. I'm going to do miles to feet first. So I'm going to take how far I'm going, which is 125 miles. I'm going to use my equality here and the appropriate conversion factor, putting miles on the bottom so that they cancel, and feet up on top. That's going to give me something like 660,000 feet, I think. That should definitely get my steps in for that day, I imagine, right? All right. Now that I do have it in feet, I could use my conversion factor, which are feet per minute. Taking my number there, 660,000 feet. Once again, we're going to use it so feet cancel, which means we do need to use it in the flip version there. That's going to put minutes up on top and 55 feet on the bottom, which is good. because that's going to now turn us into time, which is minutes. We again could see that we have minutes, and that's really 1 minute up on top. So we need to get rid of minutes. So 60 minutes and 1 hour. Minutes opposite will cancel. And now we're in units of hours. If we stopped at this point, hours are up on top. We do need to get rid of it, and we're going to go with 24 hours in 1 day. Once again here, you could, if you wanted to, kind of do each of the steps individually and get an answer. If you do that, you probably don't want to round to the very end, and then kind of clean it up at the end. Once again, we're going to multiply across the top here and divide here by what we got going on the bottom. So in this case, it's really 660,000 divided by 55 hit equals, divided by 60 hit equals, divided by 24 and hit equals. That's going to give me 8.333, a bunch of threes, days. Yeah. Significant figure wise, where should I end up? How many significant figures? 3? 3 sounds correct. So let's see why it is 3. First off, I'm not going to worry about this one, right? Because that's an exact number. I'm not going to worry about this one, which is an exact number. I am going to worry about this one, right? Because that's just from the problem, and that has 3 significant figures. This number should have how many? It actually should have 3 significant figures based off of the original number that we converted. Although I didn't write in 3 significant figures, technically this should end up right about there at 3 significant figures, which means even though it only has 2 the way we wrote it, it should have 3, and that is why we should end up with 3 significant figures here at 8.33 days. Yeah. Question on that. So again, I obviously didn't round. I could have wrote that in scientific notation if I wanted to, but as long as I kept track that originally that number up there should have 3, that means that really 3 is the smallest that we see in all these calculations, and that's where our answer should end up. Any questions on that there? All right, say look at one other type of conversion here before we move on. I think, let's say we had 96.25 cubic centimeters, and I want to know how many cubic feet is that? So you can use the same kind of conversions. 1 inch, as you should know, is 2.54 centimeters, and hopefully 12 inches is 1 foot. All right, so see what you come up with. I'll do it as well since I made it up. We will end up in the same spot. Okay, so let's take a look, see how we're doing. So obviously we want to go from cubic centimeters to cubic feet, which by the way are volumes, right? Those are cubic or cubed lengths. But we can use our length sort of equalities to do our conversion here. So we could take our 96.25 cubic centimeters, and we basically could use our centimeters to inches conversion here, because we could go from centimeters to inches, inches to feet, cubic in all those cases. That will give us opposites. 2.54 centimeters is 1 inch. If I just do that, is that the conversion? That's only going to take care of one of the 3, right? So you technically have to do this not once, not twice, but technically you do need to do it 3 times, right? And that would 1 centimeter, 2 centimeters, 3 centimeters, going to take care of all 3 of those centimeters. Now, if I multiply up on top, that's going to be cubic inches, right? I got inches times inches times inches, which means I then could go from inches to feet. Also need to do it 3 times basically to get us to the proper units. So inches are up on top. We'll do 12 inches is 1 foot. 12 inches is 1 foot. I'm going to try to squeeze it in there. 1 foot is 12 inches. Inch on the bottom, inch on the bottom, inch on the bottom takes care of all three of those. We will multiply all the way across the top, which is essentially 1, and divide by everybody gives us 96.25 divided by 2.54, 2.54 one more time, and 2.54 one more time. Divided by 12 once, divided by 12 twice, and divided by 12 one more time gives us 0.3399 cubic feet in this case, right? Question on that. Now, can you set it up like this, which might be your question, and maybe you did it this way? The answer is yes, if you don't screw it up. Yes, and I will tell you that most people will set it up like this on the bottom, will square units or cube the units, but never touch the number and only do the number once. So sometimes it's easier to write them all out. So you see visually, I need to do it 3 times. Super common mistake. People will write it like that, like I said, and just kind of take care of the units and not really do the cubing part of the number. So perfect bottom, as long as you remember to actually do the math correctly. Any questions on that there? Question on conversion. So once again, you need to show it like this. Dimensional analysis to units, to proper setup. And that's what means by proper setup, correct number of significant figures, which by the way, in this case, everything is an exact number except for our original number, which had 4 significant figures. And that is why we went to 4 significant figures here on our answer. Once again, conversions, equalities are not going to be provided for you. So you do need to know those guys, yeah? Any questions on any of that there? Yeah. So the last thing in this chapter is density. And density is defined as the amount of matter in a given volume of a substance. Differences in densities determine, for example, whether something will sink or float in water. If something is more dense than water, it will sink. If it's less dense than water, it will float. The density is equal to m divided by v, but the density of water, which is liquid water, if you ever need it, is 1 gram per milliliter. And that's sort of a constant. You should know, and as you probably will know throughout this semester, density does change with temperature. So although we usually in a problem, if you come across a problem and they're like, hey, you need to use the density of water, 1 gram per milliliter is, and that's liquid water, by the way, 1 gram per milliliter is actually the value that you would use. In reality, density does change with temperature. Speaking of water, right? Water is an unusual substance in terms of like density. Solid water is actually less dense than liquid water, right? And that's why when we put ice cubes in our cup, they float to the top because they're actually less dense than liquid water. And that is because, as we'll talk about a little bit through some chapters, when water comes together in the solid form, because of hydrogen bonding that it does as they come together, it actually creates a lot of really open space between the different water molecules. They really can't ram themselves. They get really tight to one another like most substances. They actually keep a pretty good distance between them. And if you just look at the density formula, which is mass over volume, because they keep a pretty good distance between them, the volume of ice is actually larger than the volume of liquid water. So if you take a small number divided by a larger number, you actually will get a smaller number for the density of ice versus liquid water. Where in the liquid phase, water actually could get much closer to one another, and it doesn't have as big of a sort of bloated volume as you see with ice. And that's an unusual substance or characteristics of a substance, as most things are more dense in their solid phase than say in their liquid phase.